will look painful. Okay, so in order to determine the limit of the Riemann sum, we have to determine three preps. We have three preps. We cannot jump and say, oh, the limit of what? No, we cannot do that. We have three preps. Prep number one is delta x. As we know, b minus a divided by n being the number of subintervals. So 2 minus 0 is 2 over n. So I have this piece. That's done. Now I have to find this piece, xi. And you can say xi, what does xi mean? Okay, so here is our interval between 0 and 2, because that's where the function is, and this is the area under the graph between 0 and 2. So I start here and I end here. So what is delta x? This number, whatever it is, I don't know, 2 over n. So this is my x1, and this is 2 over n. This is 2 over n, and I get to x2. This is, again, 2 over n, and I get to x3. Dot, 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 3 dots, and I got to xi. And then I got to xi plus 1. And then I get to xi plus 2. Dot, 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 and I get to xn minus 1. This is x minus 2, xn minus 1, and finally x sub n. What does this mean again? Remember, the function is up here. So I determine the height for x1 plus base times height for x2 plus base times height for x3 plus base times height for xi plus base times height for xi plus 1 plus xi plus 2 plus xn minus 2 plus base times height at x minus n minus 1 plus the last one. Because n approaches infinity, it doesn't matter if I use the leftmost point, the rightmost point, the midpoint. They are infinite. Who cares? Nobody cares anymore because I have so many. And they go to infinity. But I need to determine this. So what is x1? 0 plus 2 over n. So let's write that. 0 plus 2 over n. What is x2? 0 plus twice. 0 plus twice 2 over n. Better written as 0 plus 2 delta x. So this is 0 plus delta x. But I need xi. Can anyone tell us how to write xi? x1 is 0 plus 1 delta x. x2 is 0 plus 2 delta x. x3 is 0 plus 3 delta x. x4 is 0 plus 4 delta x. But I'm here at xi. How do I write xi? Very good, of course. That's it. 0 plus I delta x. I need this generic. Why do I need this generic? Because it's here. I need to put it in the function. That will be my third prep. So now let's finish up the second prep. It's not done yet. So then the second prep again, xi equals 0 plus I 2 over n. Because it's 0, I'm going to write 2I over n. Done. So in prep number 1, I have 2 over n. In prep number 2, I have 2I over n for xi. Finally, last prep, f of xi, which is f of 2I over n. And remember, I'm going to write the function here one more time, x squared plus 1. I plug this in here. So it's 2I over n everything squared plus 1. I have to simplify it. So this is 4I squared over n squared plus 1. So I have all my preps that I needed. Again, delta x, 2 over n, xi, 2I over n, f of xi, 4I squared over n squared plus 1. Okay, now, finally, I shouldn't say finally because it's not finished, I can write the exact area, limit, as n approaches infinity, from the sum of delta x, 2 over n, times f of xi, in parentheses, of course, 4I squared over n squared plus 1. Yes, of course, from I equals 1 through n. This is great. But now I have to continue finding it. I have to simplify this to the max and then apply the limit. And when I apply the limit, I get whatever. So at this point, I have to dig deep and go back to my properties. A constant will go outside. This is a constant. How do I know it's constant? It doesn't depend on I. This is not constant. It depends on I. But this is a number. It doesn't depend on I. It will always stay the same. We put it in front. That's our first step. Then the second step, the sum of this term plus the sum of this term, according to this. Sum of the first term plus sum of the second term. We're not going to do it all at once, so you can see it step by step. So first step, I move this in front of the summation notation or sigma notation. Then I have the sum of this, 4I squared over n squared plus 1, from I equals 1 through n, of course. How am I on time? Okay, I hope to finish, yes. Okay, limit. As n approaches infinity, 2 over n. Now, the sum of two terms, two generic terms, is the sum of the first plus the sum of the second. This is one of the properties we just looked at. I equals 1 through n. 4I squared over n squared plus the sum of 1 from I equals 1 through n. I hope you're going to watch this again because it's a lot to take care of. Okay, now my next step. I will replace this by this. We have it. Okay, so this will eventually be replaced by n. Now, this is another property. A constant in front goes outside. What constant? This is a product. So this is a constant. A constant times I squared. So this goes in front of the summation notation out here. Constant. Okay. Which page am I on? Okay. So now limit. As n approaches infinity, 2 over n. 4 over n squared outside. The sum from I equals 1 through n, oops, from I squared. This already is replaced by n. But now I know this. How do I know? It's right here. If I can get back to it. n plus 1, 2n plus 1 over 6. I recommend always multiply where is okay. So always multiply these two. So 2n squared plus 3n plus 1 divided by 6. So it's better if you have them already multiplied. Okay, finally, I continue up here, down here. So the summation notation is gone. So I have limit. That was my first step, my first target. 4 over n squared times this, because I have to replace it, and 2n squared plus 3n plus 1 over 6, and plus n. And now you see how this becomes a limit. Okay, from this moment on is just algebra and then applying limit. So I'm going to simplify all this and then apply the limit, and it's done. Limit as n approaches infinity, 2 over n. 1n will simplify. I can even simplify by 2. I find that the least common denominator is 3n. I'll distribute 2 in here. 4n squared plus 6n plus 2. And of course I need to multiply, because this is over 1. I need to multiply it by 3n. Combine like terms, multiply these two. So don't forget the limit. We are not dropping the limit operator till the last step. So now the denominator becomes 3n squared. I have here 7n squared, 14n squared, plus 12n, and plus 4. We know this from a long time ago. L'Hopital's rule is infinity over infinity. Differentiate. Limit as n approaches infinity, 28n plus 12 divided by 6n. Still again, infinity over infinity. I differentiate, I get 28 over 6. Simplify to 14 over 3. Any questions? And this is it. Exact. Now I'm going to show you, I know it took 3 pages, but I also had to explain, right? I had to explain the preps. I had to show how we determine the preps. I had to show how we simplify this, we clean it up with constants going outside and identifying the sum of I squared, the sum of I, which is n, the sum of 1, which is n, and then just algebra, combining like terms, differentiating twice using L'Hopital's rule. And no, I don't want to scare you. We're not going to do this. We're going to do it on simple problems like this, like linear, quadratic, or cubic. But now I'm going to anticipate one thing from this chapter so we can check that. How do I check that without all those 3 pages? And I'm going to explain this in detail. I'm just going to show you, just give you a taste, a warm-up on it, and I'll stop. The exact area, which is the limit as n approaches infinity, as we had from this sum, from delta x, f of xi, from I equals 1 through n, the limit of the Riemann sum, can also be determined in a different way with something called definite integral. That's why I didn't want to even say the title of the chapter is integrals. But there are different types. There are 2 different types. So this is a definite integral. So now we're going to use the the Roman S, normal S, but we're going to stretch it. It still stands for sum, but we're going to stretch it. So I'm going to stretch the S, the sum. Remember, the interval was from 0 to 2, from, of course, f of x dx. Same idea. I'm going to explain all those steps again after the test. So f of x, not f of x, I'm sorry, f of x dx. I didn't mean to put the 1 in there. So f of x dx. So this is the integral, the definite integral from 0 to 2 from x squared plus 1 dx. And I will explain after the test. This equals the antiderivative. We know how to find the antiderivative. X to the third over 3 plus x. X to the third over 3 prime is this. X prime is this. From 0 to 2. And I'm going to explain after the test that this value is determined by plugging 2 and subtract when I plug in 0. It happens that is 0. 3 times 2 is 6 plus 8 is 14 over 3. This is what we're going to deal with. But we will have examples, more examples on how to calculate the limit of the Riemann sum. But we are going to determine the areas on the graphs, and you will be able in Calc 2 to determine areas enclosed between or among graphs using the definite integral, which is a stretched S. This is still the lower limit, the upper limit, and the same thing. It's exactly the same. It's the sum. So the limit in this is a sum, these two together, of f of x dx. So everything is the same. These two concepts are in here now, the limit and the summation notation.